Hi, it is for project 1 entitled mCLESS. Some machine learning algorithms are considered as black boxes because they are sufficiently complex and not straightforwardly interpretable to humans. Such a lack of interpretability can undermine trust, particularly in healthcare, in which so many decisions are life and death issues. Interpretability is quite important. Why it is important? Once the algorithm is interpretable, then we can understand the strengths and weaknesses of the model quite easily, and we can get better feedback, and we can get enhanced probability of adoption and success. And also, most importantly, we can get insights. Here, through the project, you will develop an interpretable machine learning algorithms and formulated with least squares error, so that quite easy to understand. And we call the algorithm the multi-class least error square sum. So here, mCLESS, C-L-E-S-S is Scottish class. And now, after developing the algorithm, we'll compare it with traditional methods for various data sets. Okay, here we have a review for simple classifiers. Perceptron or Nonline is the simplest artificial neuron that makes decisions for data sets of two classes by weighting of evidence. Here we have input vector, and now we train weight and bias, and then the net input is made. So that is now weighting of the evidence. That evidence is weighted to get the net input, and through activation and along with thresholding, we can decide. When here logistic sigmoid function is chosen for the activation, then resulting classifier is called the logistic regression. So simple classifiers are making prediction with weighting of evidence. That's the bottom line. And also, this equation is representing a hyperplane, and more complex neural networks can be built by using this simple one as a building block. And machine learning is trained weights from data sets of an arbitrary number of classes. Now, the weights must be trained in such a way that data points in a class are heavily weighted by the corresponding parts of weight. Now, the activation function is used in order to keep the net input restricted to a certain limit, so that we can deal with the quantity more conveniently. But really important reason we are adding activation function is to add nonlinearity to the network. For instance, by using this logistic sigmoid function, we can add nonlinearity. Okay, here now we'll describe the mCLESS classifier. Okay, we may consider it as a two-layer neural network, and input and output. There's no hidden layers. here to describe the algorithm effectively, we exemplify this synthetic data set having three classes, red, blue, and cyan, and each class has 100 points. Now, the data, a point in the data can be expressed in this way, and if it belongs to C class, then mathematically we can write in this way, or here, and because it's a two-dimensional data point, x1, x2, and that is class label. Now, for the data set, and we have to train a set of weights, and in this way, the points in a class are heavily weighted by the corresponding parts of weights. So here, now the superscript indicates the class. So therefore, now J with W0J, W1J, W2J, that is the corresponding weight for J's class. And now, if ith class point is coming, then now when they are the same, ij are the same, then we may say there is 1. So it's heavily weighted. But if they are not the same, then the value is 0. So along with this Kronecker delta, we can express this observation. Point in the class R heavily weighted by the corresponding parts of weights. Now, the weights can be determined by the least squares method, and we call the algorithm mCLESS. Here, we'll try to represent this, the weighting mechanism algebraically. So here in training, we have a data set, and xy, x is now points, and y is the corresponding label. For that, here, first we can formulate information metric by adding column of 1. The reason is that here, and now W are unknown, then algebraically it's the same as now 1, x1, x2, and okay, I write down here, the left-hand side is the same as basically here 1, x1, x2, that row vector times here column vector, that is a W0, W1, W2, right? So here we have to add 1 in front of the data points. That is information metric. And you can do it in Python quite simply from NumPy, the column step, and you make 1, so that column, and then x is just a step, okay, so that you can put in this way to get a. Okay, now weight metric is organized in this way after learning. Once you learn, then such weight metric will be produced. Now, for right side is a source metric, and that one we have to make an algebraic formulation for that. So here we have for that data set, synthetic data set, we have 3 classes, so that the source, the metric B will have 3 columns. And then now, once the point is belong to here ith class, then ith component will be 1. like that, so that here the source metric will be now n by 3 metric, and then here delta Cij, ith row class n, now j is the same, then here that is 1. For example, this ith point is in class 0, then the ith row of B is 1, 0, 0. It's belong to class 0, is indicating is belong to class 0, and then now that is heavily weighted quantity, and for others it is 0. It is a kind of a one-hot encoding technique. Okay, so along with A and B, here we formulate the minimization problem called the multi-column least squares problem. So AW minus B, the norm, L2 norm squared, is minimized, and the minimizer is W hat. Then by using the method of normal equations, we can get it quite easily. Here A transpose can be multiplied, and then the inversion of that metric will make here W hat. For the training, the output is the weight metric W hat. And the normal metric, A transpose A, is occasionally singular, particularly for small data sets. In this case, the problem can be solved using the singular value decomposition. Now, in prediction, here, we can do it quite simply. Let x1, x2 be a new point. Then, the same way, we are making the 1 in front of the point, so 1, x1, x2, and W hat, the trained weight, will be multiplied, and then we have 30 values. So among these values, we'll try to choose maximum. For instance, from NumPy, argmax will be used to get here the C. So that once P0 is largest than, now C will be 0. Okay, ideally, if the point is in class J, then Pj must be near 1, and while other values should be near 0, because we formulated the problem in that way, so that here the Pj must be the largest. So by using such the argmax, you can decide the class in prediction. That's the idea of mCLESS. Now, for the synthetic data set, here, as a preprocessing, now data set is scaled column-wisely so that maximum value in each column is 1 in modulus. It's not the same as min-max normalization, but almost around there. Also, it's not the same as standardization, but this is one way of normalization. Now, training is carried out with randomly selected 70% of the data set, and here, after training, now the output is here W hat, and by using so that will be 3 columns, so that now by using each column of W, and we try to make the line here, Lj is 0 and Lj is 1 is now plot here. Okay, for this red class, now once is class 0, now L0, 0 is this one, and L01 is this line. For blue one, there's class 1. Now L1, 0 is this line. L1, 1 equal 1 is this line. For the final class, here L2, 0 is this line, and now L2 equal 1 is this line. So mathematically, like that, it is passing the common points. You can prove that mathematically. And if you look at this one, and then because in prediction, you are choosing the argmax, so that it looks like one versus rest algorithm, so that around the center of this triangle here, practically it'll happen, the classification will happen. Now from the center you can make a line, and again over there again such a line, and then such a line, so that is basically here now the classification, the boundary. So in this way, the algorithm is working so that because we are based on least squares formulation, it's quite easy to understand, and eventually it is interpretable. And the algorithm was run 100 times with randomly splitting the dataset into 70-30 parts, respectively for training and prediction. And that running experiment results in 97-87% in averaging and 0.00171 second in computation time in averaging. I used a laptop of Intel Core i7 and at 2.6 gigahertz. Okay, so far the mCLESS is linear classifier, and as for other classifiers, its nonlinear expansion begins with a data transformation, more precisely future expansion. For example, support vector machine replaces the dot product of future vectors with the result of a kernel function. So that here, rather than future expansion and dot product, and kernel function is used there, such a technique is called kernel tree. But anyway, the main starting point is future expansion, and try to add nonlinearity for support vector machine. However, the mCLESS does not incorporate such dot product or any kind of a similar structure. So as a result, we have to perform future expansion without a kernel tree. So practically, we have to expand the future space by adding one or more the columns. Okay, here, future expansion for mCLESS. That is original data point in D dimension. Now, here the weight, and if you are adding one column as a function of this point, here now, sigma x, then correspondingly, the weight will have one more component, w d plus 1. So here, now when you are considering algebraic system, you may start with this one, 1 and xi expanded, one feature expanded, that will be now 00 plus up to there, that is original net input. Now we have one more term and delta ij. Now this the corresponding algebraic system can be made in this way. A is now 1 and this portion is x, and then that is future expansion. However, B will be the same, and source metric is the same. And if you are solving the problem by using the normal education method, then you'll have one more row in weight metric. Each column is representing the weight for the class, so that it is for the class 0 and class 1 and so on. Now, up to this one, that is original weight. Now you have one more, automatically one more will come out. Okay. So here, by using the method of normalization, you can get it, and you will get this W tilde expanded the weight metric. So you may use various feature functions, sigma. Here, for simplicity, we'll focus on the feature function of the form. So by choosing a point P for every point x, for each point x, we try to use the distance from the special point P. So the x minus P 2 norm is added to, at the end here now, extra as an extra column. So if we do that way, then now here we may get better, for the good choice of P, we may get a better accuracy. The question is, how can we choose such P such that now by adding column, another feature, and the algorithm improves the accuracy? That's the question. But the major, the principle for future expansion is that once the data is transformed into higher dimension, then the transformed data must be more separable. So that's the major requirement and major principle. So that if you are focusing there, then you can find easily P. And also you can find here different measures, so that you can improve the performance of this the mCLESS nonlinear version. And mCLESS start from very interpretable mathematical formulation. So its nonlinear version is also interpretable and quite easily understandable. Okay, here I attached the script for the generation of the synthetic data. Okay, here, and there are two files. You can copy and paste and run in the computer. Then you'll get the data file and also a picture, like in this figure. Okay, let's go back over there. In fact, okay, here, this picture will be produced, and then also corresponding the data will be saved into a file. Okay. Okay, here we go down, and here we have what to do. Okay, implement mCLESS and training. here you should implement modules for each of the equations over there, and then use X train and Y train to get an A and B. Also, try to test, use the same module to get now A test from X test. You can get A test by here adding 1 in the beginning, and then here for prediction you can A test and W multiplication, then you can get P, and among them here now try to get here argmax, then that will be a prediction, and you can compare with the Y, the label, and so that you can measure the accuracy. And for the work, and you have to use synthetic data sets, and already we have one data, and if you're using line A rather than line 7, okay, look at here now, okay, here, and right now we are using line 7, so that scale and transformation, this is making the data set of a form over here, and now there's a long one, and here like that. If you use line 8, then you will have data and here and here and here like that, so that in the center is almost collinear, so that for any algorithm, your accuracy will be much worse than the other case. But by adding some extra column in future expansion, you may make this data set in 3D more separable, so that nonlinearity is here well working along with additional column. Okay, and also you may get here 2 data set from public domain and from scikit-learn here data sets, and by using method here you can get iris and wine data, so that I want you to test the algorithm at least for these 4 data sets. And here, after that, you may compare the performance of mCLESS with those of that algorithms. I chose here logistic regression k-neighbors classifier, that's KNN, and here SVC, that is now supported vector machine, here gamma 2 and c equal 1 means that now that parameter is for soft margin, and then gamma is 2 means that is along with Gaussian kernel, so it is a nonlinear supported vector machine. And here the finally random forest classifier. So by using these 4 of them, and you can compare the performance of mCLESS. Okay. Now, number 4 is optional for undergraduate students. If you are a graduate student, then you have to do it. And add modules for future expansion. So for undergraduate students, you can do only the linear mCLESS, but for graduate students, you are required to do nonlinear expansion. Now, for this, try to an interpretable strategy to find an effective point P. If you are choosing P arbitrarily or meaninglessly, then the accuracy will not be improved. However, if you are choosing P very nicely, then as a matter of fact, the mCLESS is the best. The mCLESS will win these algorithms for this data set. mCLESS is the best one among those algorithms. And if you are choosing more algorithms from scikit-learn, and for instance 10 and 15 algorithms, and now then again mCLESS will win those algorithms in most cases. So even simple, but because it's interpretable, you can get much better algorithm simply by adding linear distance from the point to a specific p. So it is really wonderful. You can see that. Now, after doing this experiment, report your experiment with code and results. You may start with machine learning model code in section 1.3. Earlier, we learned it here, so that here machine learning model code is here. Try to use that, and some required position you can add that for that one. For this position, you may try to import the corresponding file, and then here use this one for training. Okay, and then now for, okay, where is that? Now for that already is defined, so that training and now here in testing prediction, you can use your own algorithm. Simply change this portion, then it'll work. Okay. Okay. Let's see if I covered everything. Okay, I covered everything for the project. Thank you.